Okay, so you've already looked at the formula for the variance and the standard deviation of a binomial distribution. The variance is just NPQ. It's lovely and simple. So the standard deviation will just be the square root of that. And you do have this on your reference sheet, and you've seen how to apply this formula. But where does it come from? Well, you don't need to be able to reproduce this proof in an examination setting. So you probably also don't need to even write this down. But it's something you can sit back, relax, and just watch as I prove it, so that you have a bit of a level of confidence that this formula does work and it comes from something sensible. Now, as with the proof for the mean, there's a couple of times that it takes a little bit of a leap that you might not have thought to take yourself if you were trying to come up with this formula. But thankfully, somebody clever has come up with this, and we can actually look through and see that the proof does in fact work. Now, we're going to use the second formula for variance, and this is on our formula sheet. It is the expected value of x squared minus the expected value of x all squared. Now, I'm going to take one of those leaps now. I'm going to break this up and say, hey, let's say that that's the same as the expected value of x squared minus x plus x. Now, see what I did there? I took x away, but I added it again, so it's as though it was never there. And I've just done that for a tricky little reason that will make sense in a moment. And I've kept the second part the same. Now, we've seen that if you've got the expected value of some things added or subtracted, then you can break that up and say that's the expected value of. Now, I could break this up into three separate parts here. I could do it like this, which I think you can see makes sense, okay? But I actually want to keep these two gathered together and keep that one separate. That's the reason that I've done this. So let's go ahead and do that. Let's keep these first two terms, x squared minus x, and then let's add the expected value of x, that'll be this one, and subtract the expected value of x all squared. Now, at this point, let's just remind ourselves that mu, or the expected value of x, is a formula that we've already seen. It's nice and simple, it's just NP. So this is NP, this is NP all squared, so we can sub that in on our next line. This part here we're going to do something tricky with. We're going to say this is the expected value of, let's call this x bracket x minus 1. We're breaking it up even further. Let's sub NP in here, and let's call this NP all squared. So that would be n squared p squared. Okay, now for this next bit here, let's consider our original formula for the expected value of x. We know that to find the expected value of something, we take that thing and we multiply it by the probability of x, and we add all of those together. Well, if we're finding the expected value of x bracket x minus 1, then we need to sum up all of the x minus 1s and multiply those by the probability of x. And this is the formula here that we'll need. So to consider what happens then, let's just come up with a little bit of a table. If we consider that x could be a range of values, 0, 1, 2, etc., then x minus 1 will have a range of values too. It's going to be 0 times negative 1, or it's going to be 1 times 0, or it's going to be 2 times 1. Now, I could expand these out and actually write these as individual numbers. Let's make our pattern go a little bit further. But I'm keeping them as a pattern because I can then use that to generate a different pattern. Now, assuming that my original expansion was p plus q to the power of n, the probability of x is going to be, well, if we've got x being 0, the probability of 0 successes is going to be n choose 0, p to the power of 0, q to the power of n minus 0, which is just n, and here we're going to have n choose 1, n choose 2, we can see we've got our pattern going along, n choose 3, and here we'll have p to the power of 1, p to the power of 2, p to the power of 3, whoops, p to the power of 3, I tried to do the p and the 3 at the same time, q to the power of n minus 1, q to the power of n minus 2, q to the power of n minus 3, etc. Now, as we're going to produce this next line, remember what we're really after is we're after the sum. We want all of this, which is going to be the expected value of all this stuff. Now, clearly I've made my boxes a little bit small. I want to multiply this by this and write it here, this by this and write it here, etc., etc., etc. etc. And remember, we've got another column there notionally, which is the dot, dot, dot. So instead of trying to squeeze it all in, how about we just consider that the sum of all of this is equal to, now the first couple of columns we can actually ignore because we're going to have 0 multiplied by some stuff. So this whole column is going to be 0, and so is this one because they've got a 0 up here. So let's just ignore those two terms completely, and let's add this term plus our dot, 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 and see what our pattern actually is going to be. So we're going to have 2 times 1, sorry, let's write it like this, 2 times 1, then we're going to have n choose 2, p squared, q to the n minus 2, then we're going to add that to 3 multiplied by 2, n choose 3, p cubed, q to the n minus 3, plus dot, 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 and we're going to continue that pattern on. Now, once again, like in the proof for the mean, we're going to have to do some more working over on the side. Now, we've sort of got our main working, our side working, we need side working on the side working now. Because you can see we've got a pattern here. We've actually got 2 times 1, n choose 2, 3 times 2, n choose 3. Effectively, what we've got is we've got a number multiplied by a number 1 smaller than it, and then we've got n choose the first number. So we've got something like that. So we want to turn that into something else. So let me just bring you over here a little bit further. All right, what can we do with this? Well, let's just start by rewriting the x times the x minus 1. And then here, this is going to be n factorial over x factorial and n minus x factorial. All right, what can we do with that to change the look of it? Well, again, as in the other proof that we just looked at, what you need to do with it is not necessarily something you would have thought of doing. So again, you don't have to have leapt to this, you just have to be able to follow that it does make sense. We're actually going to unroll the n factorial twice and unroll the x factorial twice. Now, the reason we'll unroll it twice is so that we can get some terms that will cancel with this x and this x minus 1, because that's the part that we want to get rid of and change into something else. So on this next line, I'm going to say I've still got x, and I've still got x minus 1, but let's call n factorial n multiplied by n minus 1 multiplied by n minus 2 factorial. So I've unrolled it twice. And on the bottom, let's unroll the x factorial twice. That gives us x multiplied by a number 1 smaller multiplied by the factorial of a number 1 smaller. So I get x minus 2 factorial there. And then I've still got my n minus x factorial. Now I've got terms that can cancel out top and bottom, and what I get is one number out the front. I've got the n minus 1 out the front instead of x minus 1. So similar to our other proof, we're changing the x's into n's, but here I've actually got n minus 2 factorial over x minus 2 factorial n minus x factorial. Now this part here actually equates to being, I've got my n minus 1 at the front, but this is n minus 2 choose x minus 2. So I've got actually a choose number there. And to just prove that actually does equal that, if I was to take this and say, look, this is n minus 2 factorial over x minus 2 factorial, to get the other term, you do the n minus 2 minus bracket x minus 2 and take the factorial of that whole thing. And clearly n minus 2 minus x plus 2, the 2's cancel, and that gives us the n minus x. So that part there becomes this n minus x factorial. So we can see there that these are in fact equal. We don't necessarily need that part now. Okay, so we can now look for where we're seeing this pattern, and we can change this sort of term into this sort of term. So here we've got a number multiplied by a number 1 smaller than it. So here clearly x is 2. And then we have n choose 2. So that whole first 3 sets of brackets there, we can change into, well, n is still n. So we're going to have n minus 1. And then we're going to have n minus 2 choose x minus 2. And if here x was 2, then 2 minus 2 is actually just 0. So we've got a choose number with 0 on the bottom. We've still got our p squared, q to the n minus 2 in that term. The next term, we're letting x be 3. So we're going to get n minus 1, and then we're going to get n minus 2, choose x minus 2, and if x is 3, then we actually just have 1 there. So we've got now our p cubed, and we've got q to the n minus 3, etc., etc. Now, we should be able to see that every single term here, we've only generated 2, but they're going to continue on. They're all going to contain n minus 1, and they're all going to contain at least p squared. So we can bring those terms out from some brackets here and factorise. We've got n minus 1 p squared, and then inside our brackets, putting everything that's left, we're going to have our choose number. So we've got n minus 2 choose 0, and then here we're just left with the terms in q, plus n minus 2 choose 1, and here we'll have p to the power of 1, q to the power of n minus 3. Let's do another term. We'll have n minus 2 choose 2, and we'll have p squared, q to the n minus 4. Now looking at what we've got in the square brackets there and seeing if it looks familiar, it does. Every single term has a choose number, n minus 2 choose something. So this is looking a lot like it could be a binomial expansion p plus q to the power of n minus 2. Now the n minus 2 being the first choose number on the top there is giving me that clue. Now a quick inspection to see if this is what we actually do have. I can do this by saying, well, this expansion here that I'm imagining it might be is going to have every term being n minus 2 choose something, let's call that r, and then it's going to have the first term p raised to r, and q is going to be raised to n minus 2 minus r. Now let's see if that's what we've got here. We've got when r is 0, we have n minus 2 choose 0, p to the 0, yeah, q to the n minus 2 minus 0, yes. For the second term, when r is 1, we have n minus 2 choose 1, p to the power of 1, yep, q to the power of n minus 2 minus 1, and yes, n minus 2 minus 1 is n minus 3. So if this whole section in the square brackets is equal to this binomial expansion p plus q to the power of n minus 2, then if we know that p and q are the probability of a certain number of successes and q is the complement of that, then we know that p plus q by definition equals 1. So this whole section here is equal to 1. And that means that our sum, remember what we're trying to find here, this sum, this is the expected value of this part, so that we can put it all the way back here in our original working. All of this is just equal to n minus 1, p squared, because the whole section in the square brackets equals 1. So we can now take this and sub it back in over here to our original working. We have n minus 1, p squared plus np minus n squared p squared. Now we just need to fiddle around with this and get it looking like that. So we're almost there. So first let's just do one thing at a time here and expand our brackets. I mean, it'd probably be easier if I put the np squared there instead of there, and now I can expand out and say I've got n squared p squared minus np squared plus np minus n squared p squared. Now I can see these two terms are like terms, and subtracting them gives me 0. So now I've got np, which is this term, minus np squared. Now that's not looking like this yet. What's the difference? This one has q in it, this one doesn't. But if I factorise this one, bring np out in front, I've got 1 minus p, and I know that q is equal to 1 minus p. So that gives me my final answer of npq. Now, this contained a few sections where we really needed to make a bit of a leap. And you might not have thought to make that leap and come up with this formula yourself. But being able to follow it through when someone else does it is quite different from being able to have come up with this on your own. You will find that if you look at proofs for formulas like these, then you get more and more comfortable just with basic skills like unrolling factorials or like trying to spot familiar things and equate them to other things that you know. So it's not straightforward, but you don't have to reproduce it. All we really need to be able to do is apply this formula and remember basics like this as well.